What's going on YouTube? In this video I'm going to show you how to use pulse width modulation to control servo motors. So first we need to understand these three important registers related directly to our board. So we have this count register, the ARR register, and the CCR register. The count register is exactly that. It's a counter that increments by 1 for every tick of the pulse width of the PWM frequency. In this case the count register is 16 bits long. So we can count from 0 all the way up to 65,535. Okay. The ARR register, all it is essentially the period of our PWM signal. And this value actually has to be within the 0 to 65,535 or equivalent to that. And the CCR register is how we're going to set the duty cycle of our signal. So now this plot down here is actually a plot of the CNT register counting from 0 all the way up to 65,535. And so what we can do is actually pre-scale this, which means we can set a period that's anywhere between here where we want our signal to end. Okay, so we can either go the whole distance here from 0 to 65,535, which would be from this 0 mark all the way to here, or we can pre-scale the frequency of the PWM down to some value. So we can have the period go from 0 to, say, this point right here, which pre-scales our count. So now the counter is not actually going all the way up here, it's only counting to a portion of that, which essentially is slowing down the PWM frequency clock. And now if we want to set some signal, so let's plot this down here. So if we take this down here, so now this right here is our period from here to here, and I'll just write this is our period. Then along this line the counter is going to be incrementing by 1 for every tick, and then if let's say we want a duty cycle of I don't know, say 1.5 milliseconds or 10% or something like that. So a 10% duty cycle means that the signal is going to be on for 10% of the period. Okay. So essentially what we have is the CCRX register is going to trigger at this point here, which we'll just say corresponds to 10% duty cycle. So on our signal down here, it's going to be 0 volts for most of the period, and then right when it hits that CCRX value, once the counter reaches that CCRX value, that's when the pulse will go from 0 to 5 volts, and then it will remain that until the end of the period. Until that point. And so as you can see here, so this is where we could have gone to this point here. So we've pre-scaled the frequency of the PWM down to this point here, and then we've set up the CCRX register to the duty cycle that we want here. So our actual signal is only going to be on for this short period amount of time. Okay. Now I have the manual from the servos that I bought. I got them from Radio Shack, which is no longer in business, so you probably won't be able to find this exact one, but most of them are the same. So as you see over here on the data sheet, you have the duration of the logic high in milliseconds, which is essentially the duty cycle of the signal. Okay, so as you can see, the duty cycle that corresponds to an angle of 0 degrees on the servo is 0.6 milliseconds, and just like 150 degree angle is 2.1 milliseconds. So this is essentially our duty cycle here. So our signal needs to be on for 2.1 milliseconds in order to achieve an angle of 150. Okay. So now if we go back to our board here, we're going to be using the timer peripheral on the ST board, which runs off the APB1 internal clock. And when it is pre-scaled, it's going to be running at 84 megahertz. When it's not pre-scaled at all, it's going to be running at half that, so 42 megahertz. Okay. So the period of our PWM signal we get directly from the data sheet. So as you can see, the pulse width modulation wave is 50 hertz. So the period of our signal is 50 hertz. And now if we want to correspond or relate that to millisecond time, it's essentially 1 over the frequency is going to be the period. So 1 over 50 hertz gives you 0.02, which is 20 milliseconds. But what we're going to do here is convert this 20 milliseconds into microseconds, so that way that we can get a finer precision when we're trying to adjust these values here. So we can go from 0.6 to 0.9 milliseconds. If we use microseconds when I say. If we use milliseconds, we might not be able to get the fine precision, say go from 0.6 to 0.7 to 0.8 to 0.9. We might only be able to jump from 0.6 to 1.2. Okay, so we're going to use microseconds to get that finer detail to adjust the angle better. Okay, so now that we have the period, we need to figure out the timer frequency that we need for our TIM peripheral. Okay, so the actual frequency of our clock needs to be, so it's running at 84 megahertz, but we need to prescale that down. Okay, so the frequency that we need is essentially the period of our PWM signal times the frequency of our PWM. So in this case, we have our timer frequency is equivalent to 20,000, which is the microseconds, times 50 hertz. So our timer frequency needs to be 1 megahertz. Okay? So in order to get a 1 megahertz signal from the 84 megahertz timer clock, we need to prescale that by 84. So we essentially take the APB1 clock, divide that by the timer frequency that we need, and that gives us our prescaler value. Okay? So we're going to be prescaling our timer clock by 84, and we're going to have a period set up of 20 milliseconds. Okay, so now essentially what we're going to have, I'll draw it right down here. So we'll have one period, which is going to be 20 milliseconds. And so let's say this is 0 volts, say this is 5 volts. So now our signal is going to be only 0.6 milliseconds to go for 0-degree angle, and 2.1 milliseconds to go for a 150-degree angle. And that's all the only angles that we can achieve, is anywhere between there. So since our period is 20 milliseconds, we're actually not using, we're not going to be switching on any values during the majority of this time. So we have 20 millisecond signal. Really, we're only going to be using up to 2.1 milliseconds of that time. So it can go from right here, which is going to correspond to 0.6 milliseconds, and it can go all the way to 2.1 milliseconds. So in order to actually control the servo, we're going to be switching between this point right here. So this is essentially our duty cycle time, is anywhere between here. Okay, so this is going to be 6.6 milliseconds, and all the way from here to the end will be 2.1 milliseconds duty cycle. Okay, so for the rest of the time we're going to be at 0 volts, and then once we reach almost the end of the period, we'll switch it on. We'll switch the signal high essentially to 5 volts, and then it'll be on for 2.1 milliseconds or 0.6 milliseconds, which corresponds to these angles here. Okay, so now let's go over to the computer and I'll show you the code. Okay, so over here on the computer I have the main.c file open. Right at the beginning you can see the wiring connections that I have set up. So I have two servos currently connected. Both of them are connected to VCC, which is 5 volts, and ground to ground on the ST board. Now the first servo is going to be connected to port PB6, which is going to be TIM4 channel 1, and then the second servo is going to be connected to PB7, which is TIM4 channel 2. So every peripheral, TIM 1, 2, 3, 4, etc., has 4 channels. So we can actually operate 2 more servos both on the same channel. The only thing is the settings that you set up for that TIM4 peripheral is going to be the same for every channel. So the prescaler, the period, and everything is going to be the same. So you can drive, but the only thing that you have control over is the duty cycle. Okay, so if you want all of these servos to be running the same period and prescale, then I would recommend keeping them on the same TIM peripheral and just using different channels. Okay, so let's go down the main.c file, and in this video I actually wrote out all the code just to save some time, and then I'm just going to walk through what everything means. Okay, so we can actually just minimize these functions that I have here. So the sysdig handler, the delay function. So here's the most important one, the configure the PWM for the board. So right at the beginning we set up the structures that we're going to use for configuration. So as in previous videos, it's always the same. So we have the GPIO init type dev, which is essentially our GPIO init structure. Now we have 2 more structures that are going to be used to set up the TIM. So we have the time base, which is going to be common to all TIM peripherals, and then we have the output control init structure. Okay, so this is what we're going to be using to set up, since we're using an output mode, which is PWM. Okay. Now the first thing that you should do every time you come in here is enable the clocks before you do anything else. So we enable both the TIM4 clock, which is, again is on APB1. Okay, so we simply call RCC APB1 peripheral and then call TIM4, so enable that clock. And the next one is going to be to enable GPIO-B, okay, because we're using port PB6 and PB7. Okay, so we have to enable the clock for that GPIO-B port. Okay, so now what we're going to do is set up the pins, set the initialization settings for those two ports, so for PB6 and PB7, which again is TIM4 channel 1 and TIM4 channel 2 respectively. Okay, so the first thing you do is set up the pin numbers. So again, we use this structure notation, so the GPIO init structure that we declared up here, dot GPIO pin. So we're setting up GPIO pin 6 and GPIO pin 7. We can just simply OR them together since they're both on GPIO-B. The mode that we're going to be using is an alternate function because we're going to be using the TIM peripheral. The speed that we're going to set up, you can play with this, but I have it set on the high speed, which is 100 megahertz. You can change it to 2 megahertz, which is the low speed. Just refer to the manual and you can see all the different speeds. They have 2, 25, 50, and 100, I believe. Then we're going to set up the output type. We're going to use push-pull instead of open drain. That's really up to you. And then we're also, for the pull-up, pull-down register, we're going to use a pull-up register, and this is simply just for safety during startup so that the pins are pulled up to 5 volts and so we don't have a short somewhere. Okay, you don't actually need the pull-up resistor, but this is just for safety. And then finally we call the initialization function past the structure that we just created here, and then we're going to be setting up GPIO-B. Okay, so that's all we need to do to set up those two pins, PB6 and PB7. Well, actually, that's not all we need to do. We actually need to configure the alternate function for the pins. Okay, so since we're using the mode is going to be an alternate function, we have to say what alternate function do we want. Okay, so we use this function here, GPIO pin alternate function configure. Both of them are going to be GPIO-B. Then we just configure the pin. So this is going to be pin source 6, and this is pin source 7. And now both of them are going to be set up for alternate function TIM4. Okay. So now we're done setting up the pins, PB6 and PB7. And so now we need to start configuring the TIM and PWM values. Okay, so I have a whole bunch of notes here that you can read through on your own, but it's essentially what I went through at the beginning of this video. Okay. So now you can see here we declared a prescaler value, and as we found in the beginning of the video, we're going to set it up for 84. The period that we're going to use is 19999. The reason I use that instead of 20,000 was because the period is going to be 0. It's going to start from 0, so it's going to count from 0 to 19999, which is 20,000 microseconds. Okay. Now we declare the prescaler, assign it to this value here, TIM prescaler. Then the next thing we need to declare is the clock division. We're not going to have any clock division because we're using a prescaler value here. And now the counter mode, you can change this to either count up or count down. So in our case, we want it to count from 0 up to the period value here. Okay. Now, so that's the base, the time base configuration. Now you can call this initialization method, time base init, pass it the structure that we just created, and call TIM4 since that's the one we want to set up. Okay. So now common timer settings between both channel 1 and channel 2 are going to be set up next. So the first thing that we're using this structure here, the OC init structure, and then the values that we need to set are the output control mode or output compare mode. And the output compare mode that we're using is going to be PWM. And more specifically, we're going to be using PWM 1. So I have here, so PWM mode 1 is set on compare match, whereas PWM mode 2 is going to be clear on compare match. And now what this means is essentially when the count register reaches the same value as the CCRX register, is going to set that value. So it's going to enable it from 0 volts to 5 volts at that point. That's what PWM1 means, set on compare match. So in this case, you want to use set on compare match if you're going to always have the polarity be, or always have the signal low, and then it's going to be active high. So you're going to be running 0 volts the whole time, and then at the time that you reach the CCRX register, which is your duty cycle, you flip that up to 5 volts. So that's going to be active high, which is set on compare. Whereas PWM mode 2, clear on compare match, is going to be if you're running at active low, so it means you're always at 5 volts, then you want it to be active low, so you're going to drop it down to 0 volts at that time. Then you're going to want to use PWM 2. Okay? And I have some comments on the side to help you better understand. So now the output state, just enable the output state. The pulse is going to be the initial duty cycle. So again, we're starting from 0 volts, so we want to maintain our duty cycle at 0. Okay, so we want to keep it at 0 from the beginning. And then OC polarity is it going to be an active high signal or is it going to be an active low signal? So again, this ties directly to this right here, to the output compare mode. So again, we can change this. So the way we have it set up right now is it's active high. So it's always going to be 0 volts, and then once it reaches the CCRX value, once the count reaches the CCRX value, it'll switch up to 5 volts. What we could do is change this to mode 2, but then we would have to change this to be active low. Okay, so we're always running at 5 volts, and then trigger active low to drop down to 0 volts. However, I just prefer to be active high. Okay. Alright, so now we have those common settings for the timer set up. Now we need to configure each channel individually, and you'll have to do this on your own as well. So what we have here, we have to set up channel 1 and channel 2 settings. So the first thing you have to call is the OC, and then just be wary of this. You have to set up OC1 in it, and then send it the structure that we just created right here with the common settings. Pass it TIM4, which is what we're setting up. And then you also have to pass in the preload configure. Okay, so enable that preload, and then it's going to be the same exact functions for method 2. It's just OC2 in it, and then pass it those structures. Then the next thing that we have to set up is the ARR register, which is the period. Set up that preload configure, so enable that. And then finally, we just can start the timer using this command right here. So enable the TIM4 timer. So that's all we have to do to set up the timer. And now inside main, what we can do is actually control the servo. So right when we come here, we set systick, then we call that method that we just went through to configure the PWM using time4 or TIM4. And now inside here, we can actually control the servo, all by writing to that CCRX register. Okay. So in order to write to, say, the first channel, we can say TIM4, and then we'll use TIM4 is essentially a pointer to a structure. So we use the arrow notation, and then we're going to say CCR1. So that means the channel 1 of TIM4. Okay, so we're going to set that to some value. So again, if you remember looking at, or actually here, you can look at the board on screen. So if you remember looking at this, the duration of logic high is 0.6 milliseconds, and we set it up for microseconds, 20,000 microseconds. So in order to get a duration of logic high or duty cycle of 0.6 milliseconds, we have to set the CCR register to 600 microseconds. Okay, so TIM4 arrow CCR1, we can set that to 600. Okay, so that corresponds to 600 microseconds or 0.6 milliseconds, which will be a 0 degree angle. Okay. And then we can do the same thing for channel 2, CCR2. We'll just set that to be the same. Then we'll delay some time to make sure that it actually reaches that point, so 700 milliseconds. And then we'll essentially do the same thing. So let's just copy that, paste that. Let's just scroll down a little more so bring it up on the screen. There we go. And paste one more time. Okay, so we can go 600, which is going to be 0 degree angle. So this is 600, which corresponds to 0.6 milliseconds. which is going to be 0 degree angle. And then we delay some time, then we can change that thing, the first servo, and we can change that to, if we look over here, say 1.5 milliseconds, which corresponds to a 90 degree angle. Okay, so we can change this to 1500, and then change this one to 1500. So they're both going to run exactly the same. Oops, I already have that. And then the last one, for a 150 degree angle, is going to be 2.1 milliseconds. Okay, so what we can do is change this right here to 2100, and that sets the duty cycle for that. So this is going to be a 150 degree angle, which corresponds to 2.1 milliseconds. And this one right here is 1500 microseconds, which is 1.5 milliseconds, and that corresponds to 90 degrees. Okay, so that's all we do. So we set it up to 0 degrees, wait some time, 90 degrees, wait some time, and then 150 degrees, which is the end, and wait some time. And then it comes back and it's going to go back to 0 degrees, and so on and so forth. Okay, so we should be able to save this. Let's come over here to the terminal, and then let's do make. Alright, so at make, now I just need to connect this to my computer. Okay. Alright, and I actually have it running already, but I'm just going to flash it one more time on here. Make flash. Okay, so now I flashed the board, and there you go, it's running. We can just hit reset. And as you can see, so it's going from 0 degrees, there's 90, 150, 0. Here, let's slow it down a little bit. So let's increase the wait time to say 2 seconds, which is 2000 milliseconds. Let's remake that, and then let's flash it. Alright, and now let's hit reset. So there's 0 degrees, there's 90, and there's 150. And then it goes back 0, 90 to 150. Alright, so that was how to control servo motors using pulse width modulation on the STM32F4. I hope that was helpful, and I'll see you in the next one.